Welcome to The Explainer. Today, we're going to break down the massive, invisible engine that powers our planet's weather. It's this incredibly delicate system that decides everything from where we have deserts to where we have rainforests. Okay, let's dive right in.
It's a great question, right? I mean, why is that? It can seem totally random, but it's not. It all comes down to this global system of circulating air, and the whole thing kicks off with one very simple fact.
You see, the sun hits the equator way more directly than it hits the poles. And that temperature difference, that's what creates high and low pressure zones. It's the spark that starts this entire atmospheric engine. All it is warm air rising, which creates low pressure, and cool air sinking, which creates high pressure.
But here's the thing. Air doesn't just move in a nice, neat, straight line from high to low pressure. No, its path is actually, it's choreographed by a couple of invisible forces.
So first up is the main driver, the pressure gradient force, or just PGF. The easiest way to think about it is that air naturally wants to move from a crowded space, that's a high-pressure zone, to a less crowded, more empty one, which is a low-pressure zone. This is the initial push that gets everything moving.
Now this is where it gets really interesting. The Earth's spin adds a literal twist to this whole movement. As our planet rotates, it creates what's called the Coriolis force, and that deflects the moving air. Now, it's not a real push, it's an apparent one, kind of like how you feel pushed to the side when you're on a spinning merry-go-round.
So the crucial thing to get here is that these two forces are locked in a constant tug of war. You've got the PGF trying to push the air straight from high to low pressure, while the Coriolis force is pulling it sideways. And the result? Well, that's the curved path of our global winds.
Okay, so now let's see how these forces come together to build this really beautiful and elegant model of global air circulation.
To really make sense of all this, we use a simplified model. I want you to imagine 3 giant, interconnected conveyor belts in the northern hemisphere and another 3 just like them in the southern. And their whole job is to move heat from the hot equator up towards the cold poles. The first one is called the Hadley cell, and it's basically like a giant atmospheric lava lamp. You've got this intense heat at the equator that causes warm, moist air to rise up. As it gets higher, it cools and just dumps all that moisture as rain, which is what creates the world's tropical rainforests. Then, that now cool, dry air moves toward the poles and sinks back down around 30 degrees latitude, creating the perfect conditions for the world's great deserts. Then, right in the middle, you have the Ferrel cell. Now this one's pretty unique because it's not directly powered by temperature. Instead, it acts like a gear in a big machine, turned by the motion of the Hadley cell on one side and the polar cell on the other. It's responsible for pulling warm air towards the poles and cool air toward the equator, which gives us the westerlies. Those are the winds that shape the weather for so many of us in the temperate zones.
And finally, there's the polar cell. This is another simple conveyor belt driven by the intense cold at the poles. You've got cold, dense air sinking right over the pole, flowing out towards the equator, and then rising up again around 60 degrees latitude, where it bumps into the warmer air from the Ferrel cell.
Now this whole 3-cell model is the ideal blueprint. It's clean, it's simple. But the real world, well, the real world has complications like continents and oceans and changing seasons. And those things create patterns that are way more complex and honestly pretty fascinating. For instance, right where these big circulation cells meet, you get these really sharp temperature differences that create jet streams. Think of these as high-speed rivers of air, thousands of miles long, that just snake around the globe and act like steering currents for our weather systems. And this is where that huge global system starts to have very real, very local consequences. The seasonal heating and cooling of land versus the sea, all driven by these bigger patterns, create these dramatic seasonal shifts in wind and rain that we call monsoons. And to see this in action, let's take a look at a specific case study. So let's zoom right in on the Philippines. We're going to see exactly how this global circulation engine creates their distinct local rainy and dry seasons. The Philippines has 2 major seasons that are totally driven by the monsoon system. They're known locally as Habagat and Amihan. And really, they're just 2 different faces of the same large-scale atmospheric circulation. But they bring drastically different kinds of weather. Here you can see the Habagat, the southwest monsoon, in full swing. It's just this massive flow of warm, moist air getting pulled in from the southwest, blanketing a huge part of the country in clouds and kicking off the wet season.
The Habagat season is defined by that classic tropical monsoon weather. You know the feeling. It's hot, it's humid, and it is very, very wet, especially for folks on the western side of the islands.
But then, the whole system just flips. During the Amihan season, the winds completely reverse, and they start bringing cooler, drier air down from Siberia and China. This is a huge shift, and it leads to what many people consider the most pleasant weather of the year, way less humidity and milder temperatures.
Okay, so it's really vital to understand the difference between that simple, clean three-cell model we started with and the complex, dynamic reality we just saw playing out in the Philippines.
That general circulation model is our fundamental theory. It explains the big picture stuff, like why rainforests and deserts are located where they are. But large-scale circulations, like the Habagat and Amihan monsoons, well, those are the real-world weather systems we actually live through. They're dynamic, they're seasonal, and they're a whole lot more complex.
This is really the key takeaway, maybe the best way to think about it. General circulation is like the planet's basic operating system. It's the permanent blueprint. But large-scale circulation, that's the software, like the seasonal weather apps that runs on top of that system. It's what creates the dynamic conditions we all live in.
And that brings us to a final thought. This entire global engine is a really delicate dance of energy transfer. And understanding how it works is the first step to asking the most important questions about our future. As we add more energy to the system by warming the planet, how might this dance change? And what could that mean for the weather, right outside your window?